So, hello everyone, welcome to this presentation. I'm Pierre-Luc Lapointe, I'm the Mechanical Group Manager for IVI, the Innovative Vehicle Institute. Today I'll be talking about how we developed a new test bench using CANoe and Matlab Simulink for electric motor testing. So let's dive right into it. A short slide describing what our organization does. So we're a nonprofit organization with a college center for the transfer of technology. It's a special kind of organization here in Quebec that's helping medium and small businesses developing all kinds of technology. Our thing is mostly electric vehicles, and since the past 5 or 6 years, autonomous vehicles as well. So we have more than 20 years of experience in the development of all kind of electric vehicle prototypes. We mostly help Quebec industries, but we do have a few projects outside of the province and outside of the country as well. So some examples of projects we worked on in the past. So yeah, we do a lot of different cool things. And one of the things we've done last year was the development of a new test bench for electric motors. So the customer was interested in comparing 4 different motor and inverter combinations. We do have that type of equipment at IVI, but it was too small to accomplish that the tests that were required. And one last critical piece of information was that a short lead time was required for the customer's global project timeline. So we really needed to have a solution fast as much as possible, and as you can imagine, reduce the cost as much as possible as well. So what we decided to do is reuse some of the equipment we have available at IVI. So we do have an high voltage DC power supply built by AeroVironment, now Webasto. So this source can climb up to 900 volts, provide 250 kilowatt of power. We decided to build a custom subframe and use off-the-shelf EV motor as a load. With that in mind, we used a standard PC, a standard laptop with a USB to CAN vector interface for control signals. And we paired that with the software, which is CANoe and some Matlab and Simulink we will dive into right away. The requirements for the software was to provide a user interface for the dyno control. We wanted to manage the power supply, the load, and the unit under test to automate most of the tests. We had to manage faults as well to make sure we would not have flying parts all over the lab. So those were temperature, speed, and voltage limits. All of those are readily available over CAN for the types of motors we wanted to use. Of course, like I said, we wanted to minimize development costs, increase reusability for other integration into vehicle, or even other tests we would do in the future. And since we're using not dyno, but electric vehicle motors, well, we would need to manage typical startup for an EV. So that would include Precharge, the safety messages and greeting messages exchanged during boot up. So that was an additional challenge we faced when integrating those pieces of equipment. So for the test setup, the software, we used a combination of Matlab Simulink and Vector CANoe. So the method we use, we really try to make the most out of the model-based design techniques we use sometimes with electric vehicle controllers design. So some of the benefits was the documentation was much easier to produce and transfer to other team members or customers. The offline simulation was a big plus during development, so that made debugging a lot easier and safer as well. So no chance to have a flying motor again, or out of control spinning shaft when debugging. The development time was significantly cut. So you can imagine my background is mechanical engineering. I worked on the bench with other colleagues. I'm no pro into structured code, so for me, Simulink was really an easier way to get around things, achieve the goals of the customer, and make sure we would have a safe and working bench for those tests. If we go into CANoe, it was our principal interface to the load. So there's this handy little panel designer we use. It's let's be honest, it's not the greatest looking, but we're engineers, so we mostly do something that's functional and then let designers come up with something more cute in the end. As for us, for our testing, all the important informations were on the panel, so we could select the different tests. We had different tabs to tune those tests to adjust limits or adjust timing if needed. We could see the voltage set points. We had a few switches for fail-safe shutdown operations. And we do like to have all the messages if we see something out of normal right away, so we can always manage the dyno and make sure we have safe operations and we don't have any bug that was not seen during development. So those messages could provide additional informations as to is there a missing wire or is there some noise on the CAN network that's not normal. So those messages would come handy. For CANoe, we use the interaction layer to manage the message timing. And we use the environment variables in the DBC files to interface with Simulink. So one quick note is I think the environment variables are going to be obsolete in future versions of CANoe. There's a replacement for that. That's because we already had some parts of the DBC files and code with those type of variables available. So we use those in our project, but there's nothing that would stop us from using the correct variables or the correct system that Vector proposes to get this thing working. So just a quick note that if you want to copy paste what we did, you might need to use a different type of variable into your DBC file. As for Simulink, so easy enough. There's a library with all the IOs you would dream of to interface with Vector. Those are standard Simulink blocks. You just need to put them into your model. Then the Simulink model is going to be compiled and included into your CANoe model for the actual testing. So there's all kinds of triggers, signal inputs. Really what we use is some outputs to CAN messages and environment variable as inputs. So we could interface with the panel and all that. But really, for someone that uses already Simulink, there's nothing new here. You can just plug and play those blocks in your model. And then what we did for the main logic is we used a lot of state flow. For those that don't know what state flow is all about, it's a state machine design tool embedded into Simulink. Really, you can design those states, set some kind of limits or timing for transitions, and we use that for pretty much everything other than continuous signals, if we had a PID or something similar. But all the initialization sequence, event management, double check on faults, torque and speed command calculations for automated testing for efficiency, as an example. all those were dealt with in Stateflow. It makes stuff really easy to just build and then debug, since you can follow which state you are at depending on what kind of inputs you have. So we made full use of that. If we go into a little bit more in detail, so the initialization sequence is similar to in Eevee. We did reuse some existing parts of code. As for an example, when the tests start here on the left, you see that the load speed and the torque are going to be both 0. We are going to call the Precharge Sequence that goes into the block on the right, where you're going to set a voltage command on our high voltage DC power source, and then wait for the voltage to be on the correct value. This voltage command, we did put some kind of rate limiter, so it would simulate some kind of precharge circuit where you have a resistance that's going to precharge the caps on the drive side. So with that, it wasn't easy enough. 3 blocks to have a precharge sequence ready. When the voltage is within the correct command and the correct value, we can then switch back to the main test block and start the actual test sequence. So that's one example of code that we did reuse. We added for some kind of battery and power electronics test in the past. So we just copy and paste those blocks into our system. On the same page, you can see we did some kind of event management with the parallel state in Stateflow. So that means that for each time step, let's call it like that, or each tick of the controller or the vector software, in this case, we would check what's the state of all those different blocks. In our case, it's only really one test at a time. So depending on which test you decided is going to run, let's say the continuous control, trying to figure out what's the continuous torque value of the motor. So this would really be the one that's driving the show. And then we, with the same page, we could manage faults as well. So the fault management is an higher priority block, yeah. So this one all it does is check, is there DTC, an error flag on the CAN coming from either one of the motors, the unit under test or the load, or from the DC power source. If the error flag is on, then we're going to enter a fail-safe mode where we ask both the unit under test and the load motor to bring their speed and torque to 0. And then we're going to be able to shut down the high voltage system and figure out what was the error, what caused it, and have some kind of feedback to the user. So as soon as you see an error flag that's within our database or within our CAN system, all of those blocks just turn to off completely, and we can just manage the motor states just to be fail safe and make sure there's no issue. Again, another piece of information, so compiling and file management is the same in Simulink as for embedded targets. So those are really well documented. There's plenty of controllers that have that kind of feature available right now. So with the correct compiler and the correct correct controller, you can actually use your Simulink code as the code for the ECU. So that's a standard procedure for Simulink. And then in the Vector CANoe, you can include this model into the node configuration. So easy enough to do, well documented, should come as no issue. So as for the results, we were able to design, build, and use the new dyno in record time to realize a series of tests. We did have efficiency, which was completely automated, continuous torque, as well peak torque, which was simple accelerations of the system. Thermal time constant, so those were really long time tests, which you want to avoid having a technician just looking at the motor heat and cool down. So the software came really handy with that. Same thing with the torque accuracy over time. Really, what took longer was the metal. So having the subframe design and build. As for the software, within a couple of weeks or so, we were able to have something functional. So we were really happy with that. Some examples of results we had. Those results are confidential, so I just put. So those are the real curves we were able to retrieve, but I won't provide the torque and speed values because those are I don't have the rights to share them. We had a lot of points to gather for the system efficiency. Continuous torque, you can see we had some kind of dips where it was interesting to compare one motor to the other. Same stuff with the peak torque. So really some interesting results that I won't be able to share completely. As for a summary of the benefits, so in our case, we had 3 units under test to test. So since those had similar CANoe interface, the only thing we had to change to realize those tests was the DBC files. So we would only change the messages, and then we could start the test right away. All the software on the Simulink side would stay completely the same. So it made for something really efficient. The algorithm, we used it in co-simulation with another simulation software for early debugging. So we used an AimSim software that's simulating all the mechanical, electrical parts, and we were able to just find what would be the issues we would face if it was some resonance in the control algorithm or something like that, or the stiffness were not correct. So we're able to address that early on. So the Simulink control algorithm for our test bench made it really easy to debug all of that early, which would in turn cut the cost. So software development cost was cut by approximately 50%. So we did some similar projects in the past. We were able to compare with both method what happened. As I said, we did have some dynos at IVI, but those were too small for the job at hand. So we were really able to compare what was happening, what was the cost for development for that. Again, model-based design made the documentation so much easier. So we had the customer with us for one day. We just showed the state flow and Simulink pieces of a software, and it was really easy to really think and together what would cause some issues or what was happening. Was it really some types of characteristics of the unit we were testing? And that was for the bench development one of the first steps we really took into model-based design at IVI. It's really opening more advanced possibilities. Example with hardware in the loop testing and simulation. So we have an undergoing project that's similar, but with higher power, higher speeds for the motor, and we do want to test the influence of some kind of load on the system and validate what's going to be the behavior of that system under certain types of load. So we're moving from really a steady state operations to more dynamic operation in the future. And this dyno was really the first step we took into that kind of approach. We do plan to have a lot more in the future of that kind of system. The problems we face, so dyno software related, nothing much. We could have speed up the process a little bit by not compiling the Simulink model. We had some issues with the CANoe Interaction layer, but
that was our own misunderstanding of how it worked. As for the unit under test we've had, it's a whole different story. So heat management problem, coolant leakage, wrong language, wrong spec. So we really faced all sort of issues, but it's really what's happening when you're tackling those types of projects. So in conclusion, I hope you enjoyed this small overview of what we've done with the dyno, how we tested our software and how it speed up the process for our testing. I'll be available for questions in the next few minutes. So hope you enjoyed and you were able to learn something this morning. Thank you.